Welcome to Section 9 of the Renal Physiology Review. In Section 9, we'll go into more detail into how urine is concentrated, with an introduction of the countercurrent multiplier and how the different features of the thin descending limb and thick ascending limbs of loop of Henle contribute to this. Welcome to Section 9 of the Renal Physiology Review. In Section 9, we will walk through how urine is concentrated through the countercurrent multiplier. As we said before, the kidney is responsible for the maintenance of homeostasis. No matter how much water and salt is taken in, the kidneys must maintain osmolality and sodium balance within a given range. Concentration or dilution of urine is essential for this process to occur. The kidney is the major route of excretion of solute and water, and it can excrete urine across a broad range of osmolality. To remove excess water, the kidney must be able to excrete a dilute urine, and to conserve water when it's scarce, the kidney must be able to concentrate urine and excrete a concentrated final urinary composition. The ability hinges on the creation and maintenance of a hyperosmolar medullary interstitium. This is a process that is often confused in medical school, and while the details are not very important for the USMLE Step 1 exam, the concepts are extremely important. Let's walk through the osmolality of the urine as it enters a loop of Henle. As we said, in the proximal convoluted tubule, sodium and water reabsorption occurs in an isoosmotic fashion. Therefore, the urine that enters a loop of Henle is isoosmotic. The thin descending limb of the loop of Henle is permeable to water only. Therefore, water is reabsorbed, but solute isn't. The urine that then leaves the thin descending limb is hypertonic, as all the water has been reabsorbed. In the thick ascending loop of Henle, the opposite is true. The thick ascending limb is permeable to solute alone and not water. Therefore, solute is reabsorbed, creating a more dilute urine. Finally, in the collecting tubule, through the influence of vasopressin, the final urinary composition can be either dilute or concentrated. When ADH or vasopressin activity is high, water reabsorption is very high, and the final composition is extremely concentrated urine. Alternatively, in order to create a dilute urine, vasopressin activity will be low and water is not reabsorbed and instead excreted into the final composition of urine, creating a dilute urine. Let's walk through this again. The descending limb is permeable to water but not to salt. Water is removed, solute remains, and increases the solute concentration of the tubular fluid. The thick ascending limb is the opposite. It reabsorbs salt and is impermeable to water. What this does is dilutes the tubular fluid, but also concentrates the interstitium. This concentration of the interstitium then provides the driving force for water reabsorption in the thin descending limb. Flows in the descending and ascending limbs interact with each other. Salt removed from the ascending limb drives up the solute concentration of the fluid in the descending limb. Let's look at it one more time. As we enter the loop of Henle, the urine is isoosmotic after reabsorption of the proximal tubule. Going down the thin descending limb, which is permeable to water alone, water will be reabsorbed. This water reabsorption, however, is dependent on the concentration of the interstitium. The concentration of the interstitium has been maintained by the thick ascending limb. The thick ascending limb, remember, has been permeable only to solute and not water. Solute is reabsorbed. The solute populates the interstitium, which increases the concentration of the interstitium. This further drives water reabsorption in the thin descending limb. This is how the countercurrent multiplier is created. This is also coupled with the vasorecta, which are the blood vessels that are paired with the loop of Henle. These blood vessels are constantly pulling both solute and water out of the interstitium. Therefore, this process will continue until the maximally concentrated urine can be formed. However, the impermeability of the thick ascending limb to water creates a final dilute urine that leaves the loop of Henle. Much of the solute has been reabsorbed. Once again, water has been reabsorbed in the thin descending limb, but the final urine that leaves the thick ascending limb, because of solute reabsorption, is dilute relative to plasma. The countercurrent mechanism thus relies on the varying characteristics of the thin descending limb and the thick ascending limb of the loop of Henle. The final concentrating activity in the renal tubules occurs in the collecting duct under the influence of vasopressin, or antidiuretic hormone. As we said, the urine that leaves the loop of Henle is once again dilute. Therefore, if a more concentrated urine is to be formed, more water than solute must be reabsorbed. If this is the case, vasopressin activity increases. Vasopressin activity stimulates the creation and the placement of aquaporins, or water reabsorption channels, on the collecting tubule epithelial cells. Once those are present, water can be reabsorbed. If water is reabsorbed, in the absence of solute, a more concentrated urine is formed. These two mechanisms, the countercurrent multiplier and the regulation of water reabsorption by vasopressin activity, are how the urine can make an either dilute or concentrated urine, depending on solute and water intake. The clinical relevance of this occurs when loop diuretics are used. As we said, loop diuretics, such as furosemide, block the sodium-potassium 2-chloride transport in the thick ascending limb. While they increase tubular flow rate, they also impair solute reabsorption in the thick ascending limb, thus the medullary interstitium is not populated with that solute. When the absence of solute, there is less of a driving force for water reabsorption in the thin descending limb. Therefore, the loop of Henle can no longer function as well as a countercurrent multiplier and a urinary concentrating mechanism. Let's do another question that reviews some of the concepts that we've gone over. The reabsorption of sodium from the basolateral surface of renal epithelial cells is attributed to which of the following? A. Sodium-hydrogen exchange. B. Sodium amino acid cotransport. C. Facilitated diffusion. D. Solvent drag. Or E. Sodium-potassium pump. The key feature in this question is that the reabsorption of sodium occurring from the basolateral surface. A through D are all responsible for the reabsorption of sodium on the luminal surface of renal epithelial cells. E, the sodium-potassium ATPase, or sodium-potassium pump, allows for sodium reabsorption across the basolateral surface by maintaining a low intracellular sodium concentration and actively reabsorbing sodium through an energy-dependent process. This concludes Section 9 of the Renal Physiology Review. The key points to remember from Section 9 are that the different features of the thin descending limb and the thick ascending limb of the loops of Henle provide the perfect substrate to generate the hypertonic interstitium and drive water reabsorption. The two different characteristics allow for the countercurrent multiplier and the concentration of urine.